Hey everyone. Today I want to talk about Euler's formula, the polar form of a complex number, and the roots of unity. So to start off, let's talk about Euler's formula. Euler's formula is a super useful formula in a lot of areas of mathematics, but especially in complex analysis. So why are we talking about it today? Well, it's going to allow us to represent complex numbers in a new way called the polar form. So the formula is as follows. It's e to the power of I phi equals cosine of phi plus I sine of phi, where phi is a real number. Great. So it basically relates an exponential expression to a trigonometric expression. Now let's see if we can use the formula to represent complex numbers in a new way. So recall from my previous videos that a complex number z can be written as x plus iy, where x and y are real numbers, right? And this way of writing complex numbers is called the rectangular form. Now recall from my modulus and argument video that we can write x, or the real part of z, to be r cosine of phi, where r is the modulus of z and phi is an argument of z. And we can also write y to be r sine phi. Great. Now r cosine phi and r sine phi look pretty similar to what appears in Euler's formula, right? Because in Euler's formula we have cosine phi plus I sine phi. So let's see if we can sub in r cosine phi and r sine phi for x and y and see if that gets us closer to something we can use from Euler's formula. So this implies that z equals r cosine phi plus I r sine phi, right? And this is pretty close to what we have in Euler's formula. The only difference here is that we have this r term sort of floating around in here. So what we should do is factor out the r term, and then we can go ahead and do a substitution. So factoring out the r term, we get that this is equal to r times cosine phi plus I sine phi. And that's exactly what we find in Euler's formula. So we can go ahead and sub in e to the I phi for cosine phi plus I sine phi. And that equals r e to the I phi. And this is what's known as the polar form of a complex number. The polar form. And so the polar form is essentially a way of writing a complex number in terms of its modulus and its argument rather than its real and its imaginary parts. Okay, so now that we've discussed Euler's formula and how we can write a complex number in terms of its polar form, I want to go ahead and discuss the geometric interpretation of the polar form. So recall that the polar form is simply r e to the I phi, where r is the modulus of z and phi is an argument of z. So let me go ahead and draw in our complex plane here. We've got the horizontal axis as the real axis and the vertical axis as the imaginary axis. And let's say that our complex number z is somewhere out here. Well, remember that the modulus of z is simply the distance from the origin to the point z. So the length of this line here is described by r. And well, the argument, which is phi in this case, is simply the angle in the counterclockwise direction from the real axis to this line from the origin to z. So this right here is phi. And this is how we can draw or represent a complex number in its polar form geometrically. We simply describe it using its modulus and its argument rather than its real and its imaginary parts. Okay, now I want to discuss a theorem that concerns properties of numbers of the form e to the I phi. So for any phi, phi1, or phi2 in the reals, there are going to be 6 properties that hold that I want to discuss. So property 1 is that e to the I phi1 times e to the I phi2 equals e to the I times the quantity phi1 plus phi2. And this is pretty much just the same as how it works when the exponents are just real numbers, right? The only difference is that we have this I term floating around, and then we factor it out at the end. All right, property 2 is that e to the power of I times 0 equals 1. And the reason for this is because I times 0 is simply 0, which leaves e to the power of 0, which is just 1. Okay, property 3 is that 1 over e to the I phi is simply equal to e to the negative I phi. And this is pretty much just the same as how it works when you have a real number in the exponent. Okay, property 4 is that e to the I times phi plus 2 pi equals e to the I phi. Now, why is this? Well, it's because of Euler's formula. Now recall that Euler's formula says that e to the I phi equals cosine phi plus I sine phi. And well, because phi plus 2 pi essentially just represents the same angle on the unit circle, when we plug it into cosine and sine, it's simply going to return the same value as if we just plugged in phi. So that's why this equality holds. Okay, property 5 is that the absolute value of e to the I phi simply equals 1 for all values of phi. Now, why is this the case? Well, it's again because of Euler's formula, right? Because we know that e to the I phi is equal to cosine phi plus I sine phi. And well, all of those points lie on the unit circle, and the absolute value of any point on the unit circle will always be 1. So that is why this equality holds. Lastly, we have property 6, which says that the derivative in terms of phi of e to the I phi simply equals I e to the I phi, right? Because I is just a constant, so we take the derivative of the exponent, which is I phi, which leaves us with just I, and we bring that down in front, which leaves us I e to the I phi. Great. So these are 6 of the properties that hold for numbers of this form, and we're about to see the usefulness of some of them in just a second. Okay, now I want to discuss numbers of another form, and we're actually going to use these numbers in the definition of the roots of unity. And the form I'm talking about is numbers of the form e to the power 2 pi I m over n to the nth power, where m and n are both integers and n is greater than 0. And so it's very crucial that m and n both be integers and n be greater than 0 in order to extract a particular property out of these numbers. And so what is that property? Well, the property that I want to show is that numbers of this form always equal 1 for any values of m and n such that they're integers and n is greater than 0. So let's go ahead and extract this property. So the first thing I want to do is expand this expression using the definition of exponentiation. So we can say that e to the power 2 pi I m over n to the nth power is simply equal to e to the power 2 pi I m over n times itself n times. And this is the reason why n needs to be an integer and it needs to be greater than 0, right? Because the only way to express this that way is for n to be a discrete value and for it to be a positive integer. Great. So let's go ahead and write this out. So we know that this expression is equal to e to the power 2 pi I m over n times e to the power 2 pi I m over n times itself n times. Right in this last one, 2 pi I m over n, and the number of multiplications here is n. Great. Now I want to use proposition 1 from our theorem to simplify this further. So I want you to notice that this expression has the form e to the power I phi 1 times e to the power I phi 2, and then we're going to have n of these multiplications. So our last term will be e to the power I phi n. And according to our theorem, this simply equals e to the power of I times the sum of the phis. So it'll be phi 1 plus phi 2 all the way up to phi n. Great. So let's apply this proposition and simplify our expression. So we can say that this expression is equal to e to the power 2 pi I m over n plus 2 pi I m over n, and we add n of these terms. So let's draw on our last one, 2 pi I m over n. And something you may be thinking as well, this doesn't exactly match the form that the theorem shows, right? It should be e to the power of I times 2 pi m over n plus itself n times, right? Well, this expression that I just wrote out above it is simply the same thing because I just distributed I into the sum. So that's why it looks like that. Great. The next thing we can do is use the definition of multiplication to simplify this exponent. So we have 2 pi I m over n plus itself n times. So that simply equals 2 pi I m over n times n. So we'll go ahead and write this in. E to the power 2 pi I m over n times n. Well, the n's just cancel out, so we simply get e to the power 2 pi I m. Great. Now we're on to the last step. The last step is to expand this expression using Euler's formula. So applying Euler's formula, we get that this equals cosine of the thing multiplying I in the exponent, which is 2 pi m, plus I sine of 2 pi m. And this is why m being an integer matters, right? Because cosine and sine, when they take in 2 pi times any integer, they return the same value regardless of what the value of the integer is. And so since m is an integer, cosine of 2 pi m and sine of 2 pi m will return the same value regardless of the value of m. So let's substitute 1 in for m and see what we get. Substituting 1 in for m, we get cosine of 2 pi, which is 1, plus I sine of 2 pi, which is 0. So we have 1 plus 0, which is 1. So we have shown that numbers of the form e to the power 2 pi I m over n to the nth power, where m and n are both integers and n is greater than 0, always equal 1, regardless of the values of m and n. Now let's go ahead and define the roots of unity. Okay, here's the definition. A root of unity is a number of the form e to the power 2 pi I m over n with m and n in the set of integers and n greater than 0. Now, something I want you to notice is that this form of number over here, e to the power 2 pi I m over n, is very similar to the form of numbers that we were just discussing, right? It's simply just not raised to the nth power. And so what this definition is saying is that any number of this form, e to the power 2 pi I m over n, is a root of unity. Now, I feel like this definition doesn't really give us very good insight as to sort of what the properties of a root of unity are. So let's read an alternative definition and then come back to this one. So alternatively, a root of unity is a complex number zeta such that zeta to the nth power equals 1 for some n greater than 0. And now we can see why our numbers e to the power 2 pi I m over n satisfy this property, because we just showed in the last section that we can raise these numbers to the nth power and they will always equal 1. So they always satisfy the property that we can find an n to raise it to such that it equals 1 and n is greater than 0. So these definitions are equivalent. Awesome. Next we have, in this case, we call zeta an nth root of unity. So what this is getting at is, well, let's say we have the root of unity e to the power 2 pi I m over 3. So we simply subbed in 3 for n. Well, the exponent we need to raise that number to get it to equal 1, according to the last section, is 3. Therefore, it is a third root of unity. So a root of unity is an nth root of unity if it can be raised to the nth power and it equals 1. Great. Now the last part is, if n is the smallest integer with the property that zeta to the nth power equals 1, then zeta is a primitive nth root of unity. Cool. Now, in the next section, let's go over an example so that we can solidify our understanding of this concept. Okay, so here's the example. We want to verify that positive 1, negative 1, positive I, and negative I are fourth roots of unity. And then we want to make sure to identify any primitive fourth roots of unity. Recall that a number is a fourth root of unity if that number raised to the fourth power equals 1. So let's verify that for all four of our numbers. Is 1 to the fourth power equal to 1? Yes, it is. So 1 is a fourth root of unity. And it's actually the case that 1 is an nth root of unity for any n greater than 0. Great. Now, is negative 1 to the fourth power equal to 1? Yes, it is. So negative 1 is a fourth root of unity. What about I? Is I to the fourth power equal to 1? Well, I to the fourth power equals I squared times I squared. And I squared is negative 1, so this equals negative 1 times negative 1, which is 1. So I is a fourth root of unity. Now, what about negative I? Well, negative I to the fourth is the same as negative I squared times negative I squared. And negative I squared is negative 1, so this is equal to negative 1 times negative 1, which equals 1. So negative I is a fourth root of unity. Great. Now, something I want to point out is that there are always exactly n nth roots of unity. So in this case, we've identified all of the fourth roots of unity because we found 4 numbers that satisfy the properties of being a fourth root of unity. Great. Now let's identify which of them are primitive fourth roots of unity. And remember that a fourth root of unity is a primitive fourth root of unity if 4 is the smallest positive integer value such that that number raised to that integer value equals 1. So for example, if we had a number a to the fourth equals 1, but we could also raise it to the third power and that equals 1, well then a is not a primitive fourth root of unity. So let's go ahead and verify that for all 4 of our numbers. So what happens if we raise 1 to the third power? Well, that equals 1, and since 3 is a smaller positive integer value than 4, well, 1 is not a primitive fourth root of unity. All right, what about negative 1? Well, if we raise negative 1 to the third power, we get negative 1, so that's not going to work. But what about negative 1 to the second power? Well, negative 1 to the second power is 1, and since 2 is a smaller positive integer value than 4, negative 1 is not a primitive fourth root of unity. Great. Now let's check I and negative I. What happens if we raise I to the third power? Well, I to the third power is I squared times I, which is negative I. So we haven't quite verified whether or not I is primitive or not. So let's check I squared. Is I squared equal to 1? No, it is not. It's negative 1. So we need to check 1 to verify if it's primitive or not. So what is I to the first power? Well, I to the first power is I, which is not 1. And since we checked all smaller positive integer values than 4, and none of them got the result 1, well, I is a primitive fourth root of unity. Awesome. Now let's check negative I. Well, let's check all of the possibilities again. What is negative I cubed? Well, negative I cubed is negative I squared times negative I. Negative I squared is negative 1, so we have negative 1 times negative I, which is I. I is not 1, so we need to check the other exponents, 2 and 1, to see if it's primitive or not. Now, what happens if we have negative I squared? Well, that's simply equal to negative 1, which is not 1, so now we need to check the exponent 1. So what is negative I to the first power? Well, that's negative I. And negative I is not 1, so since we checked all smaller positive integer values than 4, and none of them got the result 1, well, negative I is a primitive fourth root of unity. So that's an example of verifying that certain numbers are a particular root of unity and identifying which ones are primitive roots of unity. That's it. See ya.